Let's begin today's lecture, which is on theory of metal cutting. Well, last week we had a lecture on machine tools and machining operations. And in today's lecture, I'm going to go a little bit further, a little deeper into the theory of machining to see what are the governing parameters that decide the success of a machining operation, and talk about machining forces, cutting temperature, and some theory of merchant, which is very important in machining operations. Well, what we see in this slide here is a metal cutting operation showing a turning operation. And as we can see, a typical carbide insert is used in order to take the cut from this given material. Carbide inserts are specifically designed in order to take cut of various materials, mainly metallic materials. And the reason for making the insert is that the quality of the cutting tip is of high quality. It is made in a way that it can maintain its stiffness and hardness at elevated temperatures. And if we want to make the whole cutting tool just by making use of this material, it's going to cost us a lot. Consequently, what we do is to make use of a material of lower quality to be used as the holder of the insert, and the insert will be inserted on it, which is of higher quality. Of course, we pay much more for this given material compared to the material which is used in order to make the holder. And carbide inserts of different grades are widely used in machining operations. Well, taking a look at the way that a piece of material is removed. In this figure here, we can see that the work part is being cut by a cutting tool. And there are a number of angles and geometry of the cutting tool which is of importance in the success of a machining operation. The top face of the cutting tool has got a cutting angle which is called the rake angle, and the magnitude of this angle is being defined by parameter alpha, which stands for the rake angle. And as we can see, the chip which is being removed is in contact with the top face of the cutter. As a consequence, there is a high frictional force being applied onto the top face of the cutting tool. And the material of the cutting tool has got to be resistant against wear and friction. Of course, it can last to some time depending on the magnitude of the applied friction and also the quality of the work material. And here you can see the new surface of the material which is being exposed is actually made by taking the cut from the surface of the material, and the angle between the bottom face of the cutting tool and the top face of the surface of the material is called flank angle. And this cutting edge, which has got to be sharp, is the point which is actually applying shear stress onto the material in order to remove the material from the surface. And here we can see, in this slide, we can see a number of different types of single cutting tools which are often used in turning operations. There are different types of cutting tools. For example, this one here, as you can see, the whole material is made of, the whole cutting tool, is made of the same type of material, which is the case for high-speed steel cutting tools. In high-speed steel cutting tools, the whole material of the cutter is of the same type. And as you can see, there is no carbide insert being applied to this type of cutting tools. And at this cutting edge of the cutter, as you can see, we haven't got a sharp cutting edge. It's rounded. What explains this? Instead of having a very sharp cutting edge, we've got a rounded nose. What explains this? If there is a sharp cutting edge, it will be, that given point will be subjected to high frictional forces and cutting forces as well. And after a very short period of time, it is worn. And there is a change of shape and geometry. However, if we make use of a nose radius just like that, we subject a region of the cutting tool to friction and cutting forces instead of a single point. As a consequence, the cutting tool lasts longer. By the way, if there is a very sharp cutting cutting edge, which is cutting the material, what we produce would be a rougher surface instead of a smoother surface. And that's something that you will be experimenting in the lab. Those who do the surface roughness test on the lathe, they have got to make use of two different nose radii in order to make a comparison between the two. And you will realize that the one which has got a larger nose radius produces a better surface finish. And sometimes the quality of high-speed steels is no good for taking the cut from harder materials. For those type of materials, we've got to make use of carbide inserts. As you can see here, there is a shank which is used in the tool holder, and there is an insert, as I said, which is placed at the tip of the cutting tool. And there are different shapes of the inserts for different types of geometries and also for different materials. And we can insert the right material. And there are also some multiple cutting edge tools which are often used in rotational cutting tools, like milling and drilling. For this type of operations, we've got to make use of rotating cutting tools, and often there are multiple cutting edges. Which one is preferred? Single cutting tool or multiple edge cutting tool? Which one is preferred for performing cutting operations? If we have a choice. And can you say why you think that way? Well, depends on the operation, of course. But as I said, if we have a choice for a given operation, I'm not telling you which operation. If for a certain type of operation, we've got a choice of making use of a single cutting edge or multiple cutting edges, which one would you choose?
The multiple cutting edges, because it distributes the light over the distance.
Exactly, that's the right answer. Because when we've got a number of cutting edges, it does distribute the wear which is being applied to the cutting edge, and as a consequence, your cutting tool lasts longer because there are a number of cutting edges taking the cut at the same time. And you will have less frequent tool changes for the operation. And of course, when there is only one, you will have more frequent tool changes, which is not actually of interest. Okay, here you can see a number of different types of cutting, multiple cutting edges being used for in milling cutters. And as you can see, those angles of rake angle and also flank angle are present in each of the cutting edges of multiple cutting edge tools. Okay, and let's quickly review the three important parameters which govern any machining operation. For example, in this slide we can see a representation of a turning operation. And the three dominant parameters are listed here: cutting speed, feed, and depth of cut. And as we can see in this equation, which is already familiar to us, this is what we had in the last lecture. Material removal rate, which is an indication of the efficiency of the material, is being decided by multiplication of these three parameters to one another. So these are the most important parameters deciding the success and efficiency of any machining operation. I'm not saying only these ones, these are the most important ones. Of course, there are some other parameters playing a role in the success of any machining operation as well. Like what? Like making use of coolant, for example, which isn't represented in this equation. Rigidity of the machine tool, rigidity of the workpiece, type of the material of the workpiece, and also type of the material of the cutting tool. There are various parameters which do have an impact on what we get at the end of the machining operation. However, these are the most important ones. Well, roughing against finishing operations. Are these two different from one another? Of course they are. They are different. In roughing operations, what we are after is to take a lot of material, to remove a lot of material from the workpiece. As a consequence, in order to get that, we've got to make use of high feed and high depth of cut. However, when we've got high feed and high depth of cut, we've got to lower the cutting speed. What explains this? What explains this? When F, which is feed, is high, depth of cut is high, V, which is cutting speed, cannot be high at the same time. Reason? Required power. It's limited. It's limited. It's like a digging operation which a human worker performs. Depth of cut when digging the ground. If depth of cut is really deep, and feed rate is also high, what happens? The person cannot last long, right? Because there is limited power available. The same applies to the machining operation. Depth of cut is high, feed rate is high, and there is a limit for the machining power which is made available, so cutting speed has to be low. And for finishing operations, when we are after a smooth surface finish, what gives us a smooth surface finish? A lower feed rate. A lower feed rate. And also a low depth of cut gives us a better surface finish. And as a consequence, we can increase the cutting speed. Because when F and D is low, it means that we are not utilizing the power available. So we can increase V instead. Okay? So when we are taking the cut, first we've got to take a number of rough cuts when cutting depth is high and feed is high. So we are removing a lot of material. And when we are going to take the very last cut, what we want to get is a good surface finish. So we've got to lower F and lower depth of cut and instead increase V. Because the surface finish which we have got from previous steps is not important. That's just removal of the material. It's only the surface finish resulted from the very last cut which is of importance to us. Does this make sense? Of course it does. You didn't say so, so I am answering the question on behalf of yours. Yep.
On the roughing part, you have to pass can you remove materials just once, or you have to pass?
No, you can do it in a number of passes. Because as I said, there is a limit for the power which is made available. By the way, safety is another issue which you've got to take into consideration. So if you are taking deep cuts, you can take it in a number of passes. Say, for example, 5 millimeters depth of cut. You can take 1, 2, 3, and the very final pass, which is the finishing operation, could be about 1 millimeter or so in order to achieve a good surface finish. But if we want to take a depth of cut of 50 millimeters in one go, it's impossible. It's impossible. So you can still distribute it to a number of passes. Okay. And we can represent, indeed, cutting operation is a 3D operation. However, it is possible to represent this operation in 2D instead of 3D. And this is called orthogonal model and orthogonal machining, which is being used for the analysis of forces in cutting operations. Well, let's take a look at this cutting operation here. As you can see in this figure here, this is the material being cut, and we are ignoring this dimension for now. Taking a look only from this side, which is perpendicular to this surface. This is the tip of the cutting tool, this is the material being cut, and that's the chip which is being removed from the actual material. Take a look at the parameters which are introduced here. TO, which is original thickness or original depth of cut, is the depth of cut before cut is taken. And when this material is removed, the thickness of the chip is represented by TC, which is different from TO. This is the cutting tool angle, and this is the top face of the cutting tool angle. And the cutting tool, the rake angle, which is the angle of the top face, could be anything which is being represented by alpha. And we could have an alpha which is representing a horizontal surface. For this case, the magnitude of alpha is 0. Or it could be positive, moving the top surface down just like that top face, or like that. This is negative rake angle, this is positive rake angle if this is the cutting tool. Horizontal is 0, then this is actually producing a sharper cutting edge, of course, when it is positive, right? If this is the horizontal surface, when I bring the top surface down, the tip of the cutting tool would be sharper. So as a consequence, a positive value for alpha would reduce the required cutting power, machining power, because it does produce us with a sharper cutting edge. And there is an important actually angle here, which is referred to as shear angle, being represented by parameter phi. This angle does play a very important role in resultant machining parameters. And we can define chip ratio by parameter R, where we define TO by TC. And this is always less than 1. The value of R is always less than 1 because always TO is smaller than TC. And also the shear angle can be represented by this equation, which relates it to rake angle alpha and also the value of R. So this equation here does relate rake angle to phi, which is the shear angle. Okay? Now let's take a look at this figure here. As we can see, when we are removing material, what is happening is that this cutting tool is applying a shear stress along this plane, which is called shear plane. And when the magnitude of the applied stress goes beyond the shear strength of the material, what happens? When the magnitude of the applied shear stress by the cutting tool is beyond shear strength of the material, what happens? Sliding occurs and material is removed. So this cutting tool has got to apply the shear stress on this plane, which is above the shear strength of the material in order to take the cut. And if we take this small little triangle out from here and represent it right here, on the basis of that we can compute the magnitude of the change of shape, which is the length of side AC being represented by parameter gamma, which is represented here, and it is a representation of the shear strain, this distance here, and it is a function of phi and alpha. So these two angles are very important, and they decide about the magnitude of the shear strain being applied. Is it clear? Okay. Now let's do one example on the basis of the equations we just had to see how we can make use of these equations in order to do the problems of machining. In a machining operation which approximates orthogonal cutting or 2D cutting, the cutting tool has the rate angle which is alpha of 10 degrees. And chip thickness before cut, which is TO, is given. Chip thickness after the cut, which is TC, is also given. We are to compute shear plane angle and shear strain in the operation on the basis of the equations we just had. So what we are after is shear plane angle, which is phi, and shear strain, which is gamma. And I have also uploaded an equation sheet here for this lecture. As you can see, all those equations that I did show you in the slides are listed in the equation sheet as well. So what we are after is phi and also gamma. These are the ones that we had in the previous slide. Okay. Now, what do? We are after phi. We are after phi and gamma. In order to compute the value of phi, which is this, we are in need of alpha and r. R is available. R and alpha. R is available. Of course, this is given, which is 10 degrees. R can be computed because TO and TC are given. So we can easily compute the value of R for the given problem, and then substitute the value of R here, and alpha is already given. So we can easily compute the value of angle phi on the basis of this equation. Once we are done with this, we've got to compute the strain, shear strain, which is gamma, and the equation for this is given. And we have just computed phi by making use of the equation in the previous slide, and this is also given. So, by making use of these two equations, and also the equation for the ratio of the thickness, we can easily compute the value of R first. TO is given, TC is also given. Then, substituting all these values into this equation, we can compute the value of shear plane angle, which is phi, and also the magnitude of the shear strain by making use of the right equation. Okay? Well, this is uploaded on my ECU, so you don't need to take a note of, unless if you want to take your own notes. Okay. What we see in this slide is different shapes of the chip which is being produced in a machining operation. And as you can see, there are various shapes of the chip. And the shape of the chip is telling us something about governing, say, parameters in the machining operation, and the type of the material of the workpiece as well. In this figure up here, what we can see is a continuous chip which is being produced. Discrete pieces of chip which are being produced. And this is produced when material is brittle or soft. Which one gives us this type of chip? Brittle. It's very obvious. When material is brittle, cutting speed is low, feed is high, and the friction between the cutting tool and also the chip is high. That's one of the reasons that as a consequence of high friction, chip is broken into pieces. It's not continuous. Compare it with the one on the left, on the right. Compare this one with the one on the right. Here, as you can see, we have produced a rough surface finish. But here, the surface finish is smooth compared to that one. And the type of the chip which is being produced is continuous. So, what type of material gives us this type of chip? Brittle or soft? Soft. So, for ductile or soft work materials, where cutting speed is high and feed rate and depth of cut is small, which is often used in finishing operations, this is the type of the chip which is produced. For roughing operations, often this is the type of chip being produced, and for finishing operations, that's the one. And sometimes a rough surface is produced just like that, where particles of built-up edge weld themselves to the top surface of the workpiece. Meaning that the surface which is cut is smooth in the beginning, but some particles of the chip do weld themselves to the cutting tool, and after some time they are removed from the cutting tool and weld themselves to the top face of the material, which is called built-up edge. As a consequence, what we get is a rough surface. Despite the fact that we did cut a smooth surface, that's not what we have got in the end. And that happens when material is ductile and there is high friction between cutting tool and also the workpiece material, which results in elevation of the temperature in the cutting tool and also consequently in the chip and in the workpiece. And the last type of the material chip which is produced is semi-continuous, which is resulted when we are machining very hard to machine materials. Some of the materials are ductile and can be machined easily, and some of them can be cut with a lot of problems. And this is the type of the chip which is being produced for hard to machine materials. Okay. Now I'm asking you to spend a few minutes on this activity. What we have got here is actually a diagram. On the vertical axis we've got depth of cut. On the horizontal axis we've got feed. The task is to determine what type of chip do we get when we have got different combinations of D and F. For example, low D, high F, low D and low F, high D, high F. Each one of these gives you a different type of chip on the basis of what we had in the previous slide. Can you sketch the type of the chip that you are expecting to get from these combinations? High F, high D, and the combination of the two, low high and high low. And if you want, I can go back to the previous slide, which may help you in order to decide what you will get. Okay, I'm showing you the answer to this activity. Compare what you've got with these ones. Of course, I did ask you only for 4 different cases: high D and low F, low D, low F, and these ones, high F, high D, and that one, which is high F and low D. These are the 4 different combinations that I ask you to actually sketch. What you've got somehow, is it similar to the ones that you can see here? Anybody who has got similar sketches? No? What's the question of yours? No question? Okay, of course, when F is low, thickness of the chip is actually, when F is low, it is quite possible that we do achieve a continuous chip like this one, and the thickness of the D is decides about the thickness of the chip which is being produced. And when fit is really high, what we get will be discrete pieces of the chip. Okay. Now let's take a look at this slide, which is a very important slide in today's lecture indeed. Well, this is a cutting tool which is taking the cut. And this is the workpiece material. And here we can see different forces or cutting forces which are being applied to the workpiece and also to the cut. The resultant force of cutting, which is R, is being applied by the cutting tool to the workpiece. And of course, on the basis of the third law of Newton, we know that for any action there is a reaction, which is equal and opposite in direction. Fine? This is what we know from Newton's third law. So, for this force R, which is the cutting force, there is a resultant force R prime, which is in the same direction, which is collinear. Sorry, in the opposite direction, and it is of the same magnitude. And each of these forces are resolved into two forces. This force F is called friction force, and this N is normal to friction force. And of course here, on the material side, we've got R prime, which is also resolved into shear force, which is along the angle of the plane of shear, and Fn, which is normal to Fs, or shear force. And we know that R plus R prime is 0, because this is action, this is reaction. And there are a number of other equations that I have listed here, representing coefficient of friction at this point here, which relates F to N, and friction angle beta, which can be related to mu. This parameter is called mu. And we've got shear strength, which is equal to shear strength for this given case, and we are already familiar with this equation, F divided by A, right? Is this familiar to us, this equation? It is very familiar. You can substitute tau here, which represents stress, but here we are after strength. So we make use of S instead of tau, which is shear force divided by area of shear. And AS itself can be computed by this equation, and you are familiar with all the parameters in this equation. AS is the area of the shear plane, the total area of the shear plane. Any questions on these equations? Okay. Now, let's talk about something interesting. Those forces which I did show you in the previous slide are the governing forces in any cutting operation. However, we are unable to measure the magnitude of those forces. The technology which is present today is not making us able to measure the magnitude of those forces, despite the fact that we need them. In order to estimate the required power, we need those forces. The technology which is made available to us makes it possible for us to compute or to measure the magnitude of Ft and Fc, which are being applied to the cutting tool, and the resultant force is represented by R double prime. And these are the ones which we can measure by making use of dynamometers. The direction of the forces are different. Vertical and horizontal forces which are being applied to the cutting tool. These are the type of the forces which we can measure. Question. Then how do we measure Fn, Fs, and Fn, which was shown in the previous slide? These are the ones that we can measure. Those are the ones that we need. And we can measure them. What do we do then? Well, what do we do then? You got the question? These are the ones that we are after, these four forces. Fn, Fs, F, and N. We can't measure them in an operation. But we can measure the forces which are being applied along this direction and this direction, Fc and Ft. If we can define a relationship between these forces and those forces, does it help us to estimate the magnitude of those forces? If we can define a relationship between these forces and those forces, does it help? Does it help? Of course it does. How do we do that? Are we familiar with vectors? I think we are, right? Vectors. We are familiar. If we connect these vectors, Ft and Fc, and this is the resultant force of the two in this triangle, and make use of these three corners in order to draw a circle, just like that. And then, within the same circle, we are able to draw other vectors representing F and N, and also Fn and Fs, where the length of each vector and the angle of each vector is representing the direction and also the magnitude of each of the forces. This is the thing that we are already learned, right? In engine mechanics, you have this, and maybe some other things as well. Right? So, if we can draw a figure like that, where the length and direction of each vector is representing the direct orientation and also the magnitude of each of the forces, then we can relate the magnitude of F and N, and also Fs and Fn to Fc and Ft. These are the ones that we can measure. Okay? Rectangle and phi can also be computed. That's what we just had by making use of those equations. So, if we can measure Ft and Fc and we are provided with alpha and phi, then by making use of these equations which are resulted from this figure here, we are able to estimate the magnitude of F, N, Fs, and Fn. We got that? That's the way of estimating the magnitude of Fn, Fs, and Fn, which cannot be directly measured in an operation. How does it sound? There has been a lot of work behind this to actually define these equations. There has been a lot of work behind this, but it works. Okay? Okay. Let's do a problem on the basis of this, what we had in this slide. The previous problem that we had, example 1, now we've got cutting force and thrust force which are measured. As I said, they can be measured by making use of a dynamometer. FC, thrust Ft and Fc are measured by making use of a dynamometer to be that much for a given operation. The width of the orthogonal cutting operation is also given. This is the width of the cut which has been eliminated from the 2D figure. The width of the cut is given to be W, and based on this data, we are to determine shear strength, which is S, shear strength of the work material. How can we do that? Shear strength S, the equation that we have for S. Where is it? Right here. This is the equation for S. In order to do that, we've got to compute Fs. We have got to have Fs and also As. How to compute As? The equation for As is given, W is given. We need TO and also phi in order to have it computed. Can we do it ourselves? Please spend a couple of minutes to see if you can do this. Take a note of these equations first. Take a note of any equations that you need. Then I'm going to switch to the statement of the problem to see if we can do it ourselves. We need Fs, we need As in order to compute S. What is given to us is Fc and Ft. And we can make use of any equations needed in this slide. You want me to switch back to the statement of the problem? If you have taken note of those equations that you need, then I will switch to the statement of the problem to see how we can do the problem. Fc is given 1559 newtons, Ft 1271 newtons, W is given 3 millimeters. And what we are after is S. So Fc is given, Ft is given, W is given, and what we've got to compute is S. Okay? Take a note of these values as well. Fc 1559 newtons, Ft 1271 newtons, W is 3 millimeters, and we are after shear strength S. 10 degrees, alpha. And the other thing which was given in the previous problem was phi, which we computed. Phi, which we computed from previous problem, it was 25.4. Phi, 25.4 degrees. So we've got alpha of 10, we've got phi of 25.4. And also TO, we had TO in the previous problem, which is equal to 0.5 millimeters. TO is equal to 0.5 millimeters. These are also given in the previous problem using computation of the same problem. Okay, what do we do now? Anybody who knows how to do this problem? Which one of the equations is to be used first? Which one? What are you after? Look, this is the equation to be used, right? In order to make use of this equation, you are after Fs and As. Okay? W is given, which is 3 millimeters. TO, I just said that, it's equal to 0.5 millimeters from previous problem. Phi was computed in the previous problem, 25.4. So we can easily compute As. How about Fs? Fs, there is an equation for Fs right here. We need Fc, Ft, and phi to compute Fs. Phi, we've got it. Fc and Ft are given. right? So it's not hard to do the problem. That's the way of doing it. First, make use of Fs equation. Because phi is given, Fc and Ft are given, you can compute Fs. Having this at hand, we can compute As. All the parameters are given. And eventually, it's not hard to compute S, which is that much. As I said, tau represents shear stress, and S represents shear strength. And for this given case, they are equal. They are equal. So, we can easily compute the magnitude of the shear stress for this given problem. Okay, any questions on this problem? Let's take a break for 10 minutes before we move on. Do you have my voice? So please pay attention to what is left of the lecture, everyone. Okay. Well, I have designed a homework activity for you. And I hope you like it. Nobody likes homeworks, right? Anyway, I'm not going to collect it. So it's only for your own benefit if you want to do it. What I have designed is actually an activity asking you to take into consideration what is given in this problem. Fc is given, Ft is also given. Break angle is given, and shear angle phi is also given. The same as what we had in the previous problem. We are to draw the force diagram, the circle, and those vectors representing the magnitude and orientation of each of the forces. We've got to draw the force diagram and compute the values of F, N, Fs, and also Fn for this operation on the basis of the drawing on a piece of paper. We've got to make use of the drawing instruments in order to do this task properly, and then in part B we've got to verify the validity of our results. How do we do the verification then? By using the equations. Do the computation by the drawing first, measure the values by a ruler, and then do the computation by making use of those equations. If you get the same value, it means that you've got the right answer. Simple as that. Okay? Last year, I made this a compulsory homework. This year, I'm making it optional. Okay? If you want to learn the process, do it for yourselves. It's a good idea to do it anyway. It's very interesting. Okay? Do it for yourselves. I won't collect it. And let's move on to the next slide. The Merchant equation. Well, Merchant was an engineer in machining, a well-known engineer in machining. I had the chance of meeting him in 1995 in a conference in Germany. I remember those days. There was a conference on manufacturing where in those days I was doing my PhD, and I went to that conference in order to present my paper, and he was there, and I had the chance of meeting him. Anyway, he passed away in 2006, which is some 7 years now. And Merchant did perform a number of experiments, and he developed this equation which we can see on this slide. And this equation is very useful in relating phi to parameters alpha and beta. What is beta? Beta is the friction force angle, which is shown here. This is beta. This is phi, and alpha is the rake angle. So he has been able to introduce this equation relating all these parameters to one another, which is sometimes very useful in doing the problems and computing one of the parameters when we have got two
other ones at hand. This equation is known as merchant equation. Okay? And it is telling us about what? About this angle, phi, which is a function of alpha and beta. This angle, which is the shear plane angle, plays a very important role in the resultant parameters of machining. When phi increases, AS decreases. What is AS? The area of shear. FS decreases, which is shear force, because it is a function of AS. PC decreases, which is cutting power. So the required power for cutting also reduces. Temperature of the operation also decreases. What explains all this? What explains all this? When phi increases, all the other ones which are listed in this equation decrease. It is like designing a cutting tool. When it is sharper, what happens? This is a sharp cutting tool compared to this. Okay? When you are increasing phi, this is what you are doing. You are making it sharper and sharper. When it is sharper, it's easier to take the cut from the material, isn't it? When your cutting tool is sharper, what happens? When your cutting tool is sharper, it means that the required power for cutting reduces. Temperature also reduces. And Fs and As are also function of the sharpness of the cutting tool. Now, on the basis of merchant equation, I'm going to ask you another question. The question is, how can we increase phi in order to achieve all this? It's desirable to reduce required power. It's desirable to reduce all this. And all this depends on increasing phi. How can we increase phi on the basis of merchant equation, which is given up here? Well, let's say something. We are to increase this parameter, phi, and it is a function of alpha and beta. How do you increase this then, if you make use of this equation? Well, decreasing beta or increasing alpha, right? By increasing alpha and by decreasing beta, we can increase phi, and as a consequence, it works well for us in lowering all undesired parameters. That's what Merchant has achieved on the basis of this equation. Before this, nobody knew that. When this equation is introduced, then it's very easy to say that by increasing rake angle, which is alpha, and reducing friction angle, which is beta, we can increase phi. Right? Now we know the importance of Merchant equation. It's telling us something which is important. Okay, let's do another example. Using the data and results from previous examples 1 and 2, we are to determine the friction angle and coefficient of friction. What are they? Let's go back to the equation sheet which we had. Where is it? I just lost it. Here it is. Okay. The friction angle, which is beta, is given in this equation, and coefficient for friction, which is mu, is given in this equation. In order to do that, we've got to make use of those equations which represent beta and mu. Okay? So we've got the equations. Now the problem. This is one of the equations that we had. This is Merchant equation, which we just had in the previous slide. Okay? By making use of Merchant equation, because we have got alpha and phi from previous problems. We had alpha and beta in the previous problems, right? By substituting all those values we can compute the friction angle beta easily. So, you see, by making use of friction angle instead of those equations that we had in here, instead of making use of this equation or this equation which requires F and N, if we want to compute mu, we need F and N which are not available at this time. By making use of Merchant equation, we can compute the value of beta, and when we have the value of beta at hand, it's not hard to compute the value of mu, which is requested in this problem. Okay? Well, any questions on Merchant equation before we move on to the next topic? Okay. And those equations which I have listed here are the ones to be used for computation of machining power, where PC represents the power of cut indeed, the power required for taking the cut, which is a function of FC. We know what FC is. We had this before. We know what V is, which is the cutting speed. And the gross power, what is the difference between gross power and machining power? Does anybody know? The gross power and machining power, what's the difference between the two? Say that again, please. Yeah? Efficiency. It takes efficiency of the machine into consideration. I mean, the whole power which is made available in the power unit is not to be used for the cutting operation, because there is a loss of efficiency in the whole mechanism. The whole power which is made available in the engine is not the power that you get for the operation. There is some power which is lost and converted to heat and some other things. And this depends on a factor which is represented by E, which is the efficiency of the machine tool, which is often, the value of E is often something between 90 to 95% for most of the machine tools. So the gross power is the power which is available at the power unit, and PC is the power which is used in order to take the cut. And we can relate these two by making use of E, which is the mechanical efficiency of the machine tool. As I said, it's something about 90-95% for most of the machine tools. And specific energy, which is also equal to unit power, can be computed by dividing the required power for taking the cut by material removal rate, which is already we are already familiar with material removal rate. Okay, now let's do another problem on the basis of these equations. We are continuing with those problems that we had in this lecture so far. We have to determine cutting power and specific energy, U and PC indeed. In the machining operation, if the cutting speed is that much, which is V, and we summarize data that we had from previous examples, TO, W, and FC are the values which are given. Take a note of what is in this slide, then I'm going to show you the equation sheet to make use of the right equations to do the problem. What is given to us is cutting speed 100 meters per minute, TO, which is the depth of cut before cutting, which is 0.5 millimeters, W, which is the width of cut, which is 3 millimeters, and FC, which is measured by the dynamometer, is 1557 newtons. And what we are after is PC, cutting power, and U, specific energy. These are the ones that we are after. Okay? Switching to the equations, On this side of this equation sheet, we've got the equations for the theory of machining, and here we've got power and energy equations, the ones that I had in the very last slides, plus 2 more equations for estimation of the temperature in cutting. So we had the top 3 equations in the previous slide. What we are after is PC and U. Are we able to compute PC and U on the basis of what is given in the statement of the problem? Are we? Okay. FC, is FC given? FC is given in the statement of the problem, and V is also given. So it's not hard to make use of the right equation, which is this one, right? Which relates FC to machine power, and as V is given, FC is also given. All we need to do is to substitute the values in order to compute the required power for machining operation. And next, the equation for specific energy, which is this. Have we got all the parameters to compute this specific energy? FC is given in here, V is given, and everything else is also given. So we should be able to have these computed. This V from the equation should be eliminated. This V in the denominator doesn't exist. I don't know how I have put it on. But anyway, because we've got one equation up, V up here. This V should be eliminated from the equation. It doesn't exist here. Okay? Take that off, and I will have the slide corrected, the one that I have uploaded. So FC times V divided by TO times W. That's the right equation. And substituting all those parameters, this is what we get. Okay? Okay, it wasn't hard to compute this problem because all the parameters were given. Okay. Now let's take a look at this slide here, which is talking about temperature in machining. Machine temperature is important. Machine temperature is important. Reason, what explains this? Why is it important? To know, to estimate the magnitude of the temperature which is produced in a machine operation. Why is this important? Say something, please. Don't fall asleep. Is it the time to stretch our bodies? Yes or no? Are we falling asleep? If we are, it's the time to stretch our bodies. Okay, spend a minute on stretching your bodies. We've got time. Stretch a minute on stretching your bodies. Everybody, stand up, please. Stand up, everyone. Stand up, stretch your bodies, because I'm not hearing any voices. It means that you are falling asleep. Okay, so the question again, why is it important for us to be able to estimate the temperature which is resulted as a consequence of taking the cut. Why is it important? Because so many reasons. One of the most important ones, when there is a change of temperature in the workpiece, what happens? It expands, and consequently, what you produce is not what you get. Because of the average temperature expanded, you produce something which is precise. After some time, what you measure is different. It's different, it's not what you produce. And you ask, why? It's obvious, change of temperature. So you've got to maintain temperature to a limit when the magnitude of the change of size is acceptable. If it is beyond that, then you've got to reduce the fats. So it's important, isn't it? It is important. Not just that, there is a relationship between the log of the cutting tool and also the temperature. As temperature of the operation increases, the lifetime of the cutting tool decreases. So increased temperature of the machining operation increases your cost of tooling, which is undesirable. What else? What else? I have mentioned 2 reasons so far, if some other reasons to be added to the agenda. Number 3, safety. Safety. If you lower the temperature as much as you can, you are not actually putting the machinists or people around the machine in danger. There is safety hazard when temperature of the machine operation is really high because of the chips which are falling off, and someone could touch those chips, and that happens in the workshop very often. The cut is taken, I've seen many times. Students touch it with their hand, ignoring the fact that it's hot, it's really hot, and burns the skin of yours, and that happens. That's one of the reasons that you are asked to wear gloves when you are machining the workpiece and doing any activities. Anyway, for the reasons that are mentioned, we've got to be able to estimate the magnitude of the temperature which is produced in machining. Another question, I have covered the number here. I'm asking you to estimate what is hiding here. Approximately something percent of the energy in machining is converted into heat. What's the figure which is hiding here? I didn't hear you. Say that again, louder please. 98%. Is it right? It is. Good guess, thank you. How does it sound? Impressive, isn't it? It's very high indeed. And that's true. 98% of the energy in machining is converted to heat. So, that's the reason that we need to lower the temperature of machining by making use of a mechanism. And that's one of the reasons that cooling or some other type of cooling mechanism is used in machining operations. And take a look at the distribution of the temperature onto 3 parts which are represented in 2 sections. This is the cutting tool, this is the chip, and this is the workpiece. And take a look at the distribution of temperature. Those numbers are temperature in degrees C, which are represented. Take a look at the distribution of the temperature at these 3 sections, and the gradient of the distribution of temperature on each of those 3 as well. This is the hottest point in the machining operation. This is the tool tip, but the hottest point is not this point, it's right here, somewhere just above it. What's the reason for this? Why the hottest point is here and not here? Well, I don't hear you. Did you say something? Friction. The frictional force is maximum at this point. The force of friction between the chip and also the actual top face of the cutting tool is maximum at this point. And as a consequence, if there is a tool where because of friction, it's maximum at this point.
And that's something that we are going to talk about in the next lecture when we talk about cutting tools, materials of cutting tools, and cutting tool technology. And also, comparing the three sections of the parts which are shown here, the workpiece, the chip, and also the cutting tool. Which one is the one which receives maximum heat energy? Which one? Is it the cutting tool, or the chip, or the workpiece, which is hotter than the other two? Take a look at the numbers. Which one is this? Cutting tool. 700 degrees is maximum. Workpiece is maximum 130, the top face. And the chip itself is about 600. So it's the cutting tool which receives maximum heat energy, followed by the chip. And this one receives minimum energy. Reason is that friction occurs between these two. The friction of the chip and also the cutting tool, which produces a lot of heat energy, is between these two pieces, and that one is not involved, which is good for us. Because this is the one which decides about what is left. The geometry which is produced is this one. And that's one receives minimum heat energy. So the expansion will be minimized. And there is a simulation of the whole process. And the colors, the red color is representing the highest temperature, as you can see. That's the way a cutting is performed, and distribution of heat energy on different pieces of the cutting tool and also the workpiece and the chip is properly represented. Looks nice, right? Okay. How do we estimate the temperature? By making use of the equation which is given here, we can estimate the temperature rise. Delta T represents temperature rise. Temperature rise in the whole operation, and we are familiar with those parameters already. And parameter K is a thermal diffusivity of work material which should be given for a given operation, and rho C is representing volumetric specific heat of the work material which should be given to us for a given operation. This equation here gives us change of temperature. And there is also another equation, this one, which is Trigger's equation, which defines a relationship between temperature and V, which is cutting speed. K and M are coefficients with actually are related to the workpiece material. And this figure here is telling us the relationship between T and V. This is cutting speed V, and this is cutting temperature in degrees Fahrenheit. And as you can see, as cutting speed increases, temperature of machining also increases. And it depends on the quality of the workpiece material. And for each material, the different curve is given. However, the overall trend of the curves are similar. An increase in temperature as V increases. And Trigger has performed a number of experiments, and he has been able to restore all this information into the form of his equation. This equation is very similar to another equation that we have for I'm asking postgraduate students who have done some lectures on tool life. Is this very familiar to tool life equation? Tool life equation is similar to this. V times T to the power of N is equal to a constant value C. So there is a relationship between V, cutting speed, and tool life, and here there is the same similar relationship between temperature and also cutting speed. And this is the same equation with explanation of the parameters, which is the very last slide of today's lecture. Any questions?
Okay, and this concludes today's lecture, and I would like to thank you for your participation. You can take a break of 25 minutes, and at half past 12, we will have the mid-semester test. As I said, undergrads will be sitting in this room, and postgrads will be sitting in this another room, which is in the same building. Rooms 104 and 105 are booked for postgrads. So thank you very much for your participation, and see you at the time of the test. Okay, we are done.